so we can start. There was a question in the chat which I missed before. So the issue about reproducing results because of RAM. Well, I think the question is like whether can we run your notebook and get exactly same results that you reported. So I think at least for the validation set like that you have, as long as you fix the seed, I should be able to see the same result. So, but if the result is approximate, it's okay. Like so, you don't need to have the exact number. Okay, so let us continue. So before the break, like we looked at the idea of kernel methods, right? Like so you can take any linear model and derive the dual representation of the model, where you can represent the functional form as a dot product between the input and all the previous inputs, right? Like so whenever you have this idea of x transpose or x dash x transpose or x transpose x, then you can take that particular dot product and make a kernel out of it, and you can use any nonlinear kernel that you want as long as the K matrix is positive semi-definite, right? Like so then you can develop nonlinear versions of any of the linear models that we have used so far. Okay, now we also saw an example like by doing that with linear regression. So I wanted to also talk about Gaussian process, as you can see from the notes, but probably I'm going to skip it. Okay, so that we have more time to talk about like what are the next set of machine learning problems that you can think about. Okay, so we will not do Gaussian process, which means it's not there in the exam as well. Like so, even though you have that in the notes, but the idea of Gaussian process is really to take Bayesian linear regression and extend it to a functional view, like where you can have much nicer properties than simple Bayesian linear regression. Okay, but it is not very crucial to complete, so we will not do that today. Instead, we are going to move to the second part or the final part of the course, like so, where we are going to talk about some of the frontiers in machine learning. Okay, so this course, like, even though like it's an introductory course to machine learning, like machine learning is so broad and like wide that like it probably requires a couple of semesters for proper introduction. Okay, so there are a lot of topics that I chose to not include. Like, well, like today we chose to not include Gaussian process, right? Like so, but there are a lot of other topics that I chose not to include because the main goal of the course was really to introduce you to the breadth of machine learning, but at the same time going as deep as we can, right? Like so, which is one of the reasons why students find this course to be a little bit challenging, because we try to do both breadth and depth. Even then, like we skipped like a few really important topics which I normally would like to see in a machine learning course. Okay, so first we will talk about what is not covered. And then we will talk about like frontiers in ML research. Okay, so one of the most important topic that we did not cover in this course is the idea of reinforcement learning. Okay, but I know that a lot of you are in my oral course, so it's a good complementary course, like you are covering reinforcement learning there. But for the benefit of people who have not taken an oral course, like I just want to introduce the idea of reinforcement learning. Okay, now so far in this course we have seen supervised learning, like where you have input and output pairs you're trying to fit a function f from x to y. We also looked at unsupervised learning, like PCA, or dimensionality reduction methods, where you don't have an output, you just have inputs, and you're trying to come up with some structure based on the input, right? So there's no supervision. That's why we call it unsupervised learning. So reinforcement learning is a totally different learning paradigm. Okay, so in the case of reinforcement learning, you're going to have your algorithm, sometimes called as agent. Okay, the oral agent or the algorithm. Now, this is going to interact with the world and make decisions, okay, or make predictions if you want, but the predictions are basically decisions. So the whole idea here is you're going to interact while you're learning or acting, okay? So every time step, the agent is going to take some action. Now this action is fed to the environment or the world. Now based on your action, you're going to get some reward. And also you're going to observe the next state. Okay, in the next state, you're going to take the next action that is going to give you the next reward and so on. Okay, so this is the learning paradigm here. And the objective function for all the reinforcement learning algorithms is just one thing, which is basically to maximize the sum of rewards that it could get in its lifetime. Okay, so the goal here is actually to learn a policy. Okay, a policy is basically a function which takes state as input and gives what is the action. Okay, learn a policy that maximizes sum of rewards over time. Is that clear? Now this is very different from machine learning methods that we have seen so far, right? So far, for example, if I have to treat this problem as a supervised learning problem, if I have to treat policy learning as supervised learning, then it is basically predicting the action, right? I will give you a data set which has a bunch of states and the corresponding action. You train a logistic regression, or you train a neural network, you train whatever model you want, you have your policy, right? So that is a supervised way of approaching this problem. Now the problem with that is there are a lot of interesting problems where you cannot get the supervision. Okay, for example, let's say when you are, let's say you want to train a system to do autonomous driving. Okay, so self-driving cars. Now in the case of self-driving cars, if I have to treat that as a supervised learning problem, then I have to imagine every possible scenario the car will be in and tell, okay, this is the action to do. First of all, in such a situation, imagining every possible situation itself is very difficult, right? So there are infinitely many possible scenarios. Now, it is also very, very difficult to collect data in those situations, right? So that is a perfect example where you can benefit by having some supervision, which is not as rich as supervised learning, but a weaker form of supervision. Okay? So the idea of reinforcement learning is to give rewards instead of saying what to do. I will not tell you what action to take. Instead, I will tell you, okay, this was good, this was bad. Okay. Now, imagine how you learned to ride a bike, right? So nobody tells you you have to press with this much force. The actions that you took were pressing with some force, and balancing your body and so on, right? So now it is impossible to teach a kid by saying you have to put this much pressure, you have to be in this particular angle to balance and all those things. Instead, all you do is let the kid learn, so when it falls down, so it gets a negative reward, right? So when the kid does well, you clap, and it, he or she gets a positive reward and so on, right? So this is another example where this idea of rewards makes much more sense than having exact labels. Okay, now how to design machine learning algorithms which can take these scalar rewards as supervision instead of the actual labels. Okay, so that is the idea of reinforcement learning. It is very different from supervised learning and unsupervised learning. Okay, now if you are interested in like learning more about reinforcement learning, like of course, like I am teaching reinforcement learning, but only in every fall. So it will be next fall. But let's say you're graduating, you really want to do it now. Like, so there is also a reinforcement learning course at McGill in winter, usually in winter, but I'm not sure if they're offering it this year. So you should check, okay? But there are a lot of good online resources available. And the lecture recordings of my RL course is also available in our YouTube channel. So you can just watch that if you want to learn more. Okay. The second important topic that we should have seen, but we did not see is the idea of graphical models. Okay. Now, if you remember our discussion about naive Bayes, right? So can somebody tell me what was the assumption of naive Bayes?
Features are independent.
Independent?
Independent.
Are they always independent? They're independent given the label, right? So it's conditional independence. Like features are not completely independent. Like, so we make an assumption that probability of x given t can be written as product over I is equal to 1 to m xi p of xi given t, right? So they are conditionally independent, like the features. Now, when we talked about naive Bayes, I also told you how strong assumption this is. Like in real life, this is almost always like not true. Okay, there will be features which has very complex nonlinear dependencies. Okay, not all features are independent. Okay, so it is very difficult to have such a perfect independence case in practical applications. Nevertheless, like practically naive Bayes works really well, so you can use it even though it's erroneous. Okay, however, so naive Bayes is actually one simplest form of graphical model. Okay, so the whole field of graphical model is about how to model dependencies between the random variables. Okay, now we are interested in modeling p of x comma y, right? Naive Bayes makes a very strong assumption. Instead, what if there is some dependency between like different x's and y's? How can I efficiently capture these dependencies and develop an inference method like which would make predictions about y given x, right? So now in graphical models, you would typically represent this distribution as a graph. Okay, now this graph is going to have a bunch of nodes and connections between the nodes like this. Okay, the nodes are going to be your random variables, and the edges just mean that there is actually some dependency between two nodes. Is that clear? Like for example, let's say I have one more node which is separate here, and this node is independent of all the other nodes. Is that clear? Now, graphical models is in some sense like also described as a marriage between probability theory and graph theory. Okay, so like all the algorithms that you can come up for learning with graphical models involves both graph theory and probability theory. So graphical models are also kind of a framework, just like how neural networks are a framework to model like whatever functions that you want, right? Like you can have a feed-forward network, you can have a convolutional network, you can have a recurrent network, you can have skip connections, like you can do a lot of things with neural networks, right? Like so neural network is kind of like a template or a framework. Similarly, graphical models are also like a language for machine learning or a framework for machine learning. And if you really care about doing machine learning for career, like I strongly recommend you to take a graphical models course. Okay, so because this gives you the language to talk about machine learning, like which is very valuable. Now, if you want to do graphical models next semester, there is a graphical models course at McGill taught by Siamak in the CS department. But if you can wait for one more semester, in the fall, there is a graphical models course at UDM by Simone Lacoste Julien. So there are a couple of options for graphical models, like if you want to learn. And there is also a really good Coursera course on graphical models from Stanford, which is also highly recommended. Okay, so this is about things that we did not cover. Okay, now let's talk about frontiers in ML. Okay, now in the beginning of the course, we talked about artificial intelligence, right? So now I also told you that machine learning is the most promising way to solve artificial intelligence. Like there are a lot of non-learning heuristics based approaches, but so far like ML is dominating, right? Like so now ML I think is one of the most promising ways to achieve what some people call as artificial general intelligence, or AGI. Like so when people talk about AGI, it's like this one general purpose algorithm which is really smart, can pick up any task and solve any problems, just like how an expert human can solve many things, right? Like so now to do that, like right, like so to have a complete AI system, there are still few more problems that we should talk about than just prediction. Okay, so the prediction problem that we saw like that we discussed in detail for this one semester is definitely the foundational or fundamental problem like that a machine learning algorithm should solve. But there are many other things that are needed to come up with an AGI. Okay, so I'm going to list some of them. Like so one of the important aspect that a general purpose algorithm should have, I think, is the idea of like natural language processing. Okay, a system to be useful for humans, like it should be able to interact with humans. Okay, now sometimes it is not required. Okay, here is the thing, we are talking about general purpose systems. Okay, so like for example, if your goal is just cancer prediction, then you don't care about whether the prediction system can speak English or not, right? Like as long as it gives me a 99.999% accuracy or like F1 measure in cancer prediction, I'm happy, right? But we are not talking about such expert systems now. Like we are talking about something like Siri, but a really smart Siri. Like so something which you can talk to and it can do tasks for you and so on. Okay, so when you want such general purpose assistive technologies, I think language is very important. Like so we need systems which can understand language but also generate language. Now this is a whole field by itself, like the idea of natural language processing. The field of NLP is heavily built upon machine learning. Like there's a lot of machine learning there, but there's also a lot of non-machine learning aspects there, like linguistics and so on. Okay, now if you want to learn more about language processing, I think there are a lot of courses in Montreal. Like so there is one at Poly taught by Amal, and there are a couple of courses at McGill, like one of them being deep NLP, which includes deep learning and NLP. And I'm sure there's also a couple at UDM. So there are a lot of courses to do natural language processing. Now, the second important characteristics for such a general purpose system is vision. Okay. Now, the system should be able to see the world and perceive it and act accordingly, right? So this is the whole field of computer vision. Again, an application of machine learning. Okay, there's a lot of machine learning methods, but of course, the problem itself has its own characteristics, like which you need to consider if you want to come up with computer vision applications, right? Like so, I imagine again there's a lot of courses to do computer vision, like in Montreal, like so, both within and outside Poly. So finally, like such systems might also require robotics. Okay, I'm going to make this an optional requirement because we don't always need embodied agents, right? Like, so we don't always need physical systems. Sometimes it's completely okay for the system to be a software. Like, again, I'll go back to the personal digital assistants example, okay? Something like Alexa or Siri has to speak to you, like, and understand you, has to see things so that it can interact, but it need not have the robotic arm to deal with us, right? Like, so we can do a lot of interesting things with Siri or Alexa without having the robotics component. So, however, like sometimes like you need robotics, like for example, let's say you want really good general purpose cooking agent, like a robot that you want to deploy in kitchens. Okay, so that requires physical realization, and it requires like good grasping skills, like navigation skills and so on. Like there's a lot of hard fundamental problems in robotics that you have to solve to have such a good system. Okay, so again, I think I assume Giovanni has like a bunch of robotics courses, like, and there are a lot of robotics courses available in Montreal. Like, so at UDM there is a autonomous vehicle course which is for robotics for self-driving cars, like if you're interested in things like self-driving cars. Okay, so there are a lot of options available for this as well. In general, like one tip that I can give is like look at the Mila website for the list of ML courses. So that gives you a pretty much good idea of all the courses in ML, like that you can see in all these 3 to 4 universities. Okay, now I think these are all field by themselves. They all require a semester or 2 semester long introduction. But if I have to talk about the progress that has happened in the last couple of decades, so we have made a lot of progress in language and vision. Robotics is still, I'm sure you might have seen a lot of impressive robotics videos from, what is that company? Boston Dynamics, right? Like, so, but one thing that is often not explicit to the viewers is Boston Dynamics robots don't use machine learning that much. Okay, so it is a lot of classical planning and like heuristics. Okay, so but it is very impressive that they can come up with a general purpose robots with just planning, like a non-machine learning solution, right? But the idea of using machine learning for robotics is still very naive. There is a huge scope for research and making impact in doing machine learning for robotics. Okay? Like there is a lot of progress in the last 5 years, but it is nowhere close to the maturity of like natural language processing or computer vision. Okay? So like there are a lot of good conferences like for you to learn more about these topics. Okay, so in general for machine learning, like you should look at conferences like ICML, International Conference on Machine Learning, NeurIPS, which stands for Neural Information Processing Systems, ICLEAR, which stands for International Conference on Learning Representations. Like now, similarly for NLP, you have ACL, NAACL, EMNLP, and a bunch of others. For vision, you have CVPR, ICCV, ECCV, and a bunch of other conferences. For robotics, I think you have conferences like RSS, ICRA. There is a conference on robotics with machine learning, learning for robotics, the Coral conference on robotics learning, and so on. So these are places for you to look at to know what are the most recent progress in these topics. Okay. Okay. So now, finally, I want to talk about like what are the other machine learning problems than just prediction, right? Like so the entirety of this course was dependent on this very simple framework where I will give you some X, you make some prediction Y, and learn a function F, like which is going to make as accurate prediction as possible, right? Like so we are going to call this problem as the problem of prediction. Okay. Even though this is a fundamental machine learning problem, it is very restrictive in what can be achieved by having good prediction systems. Okay, to have general purpose agents, like we need to solve many other interesting learning problems. Okay, so we're going to see a bunch of them today. So the goal for today's lecture is really to introduce you the problems, not the solutions. Okay, so I'm going to only define the problems, and here is a very interesting exercise for you. So if you care about like doing machine learning in the future, like as a career, right? Like, so I highly encourage you to not Google or like go search about these problems. Okay, I want you to take these problems and think about how you will solve these problems. We are going to see, I think, 10. Yeah, we are going to see 10 different machine learning problems today. Okay, like I want you to spend some time. Like you have all the background knowledge, so you have the fundamentals. I want you to spend some time. Like you can even take a week to think about one problem. Okay, so pick a problem, think about how you will solve by using the techniques that you have learned so far. There's a very high chance that whatever solution you're going to come up with has already been done. It is okay. That only gives you a reassurance that you are thinking in the right direction. Okay, so this will also stimulate your like skills to think about how to solve machine learning problems. Okay, so don't Google about these problems. Like let's just look at these problems. I will not talk about solutions. Like I'll only give you the problem. Okay, so the first problem that we are going to talk about today is the idea of semi-supervised learning. Okay, now in supervised learning, like we were given a data set, let's say D, which had a bunch of xi and yi. Let's say for I is equal to 1 to capital M. Okay, and we were learning a function f from x to y. Right now, it is not always possible to collect a lot of examples to train your supervised learning system. Okay, so for example, like your examples could be costly. Like take medical records. Like every row in your example might include a bunch of tests. Each test could cost thousands of dollars, right? So examples could be costly, or your examples could be time consuming. Like to come up with a label, like maybe it requires a like very difficult process. I can give you another practical example. Like so, like for example, like in chip designs, right? Like so, like sometimes you might have faulty designs. Okay, now if you can easily capture this faulty design in the beginning of the process, instead of going through the entire testing phase, then you save a lot of time and money. Okay, now you can design machine learning systems which will predict whether something is faulty or not. However, to train the system, you have to do the entire testing process, which is extremely time consuming, and then you have the answer. Okay, so this is an example where getting a label is time consuming, or getting the label might require experts. Okay, and experts are rare. Okay, these kind of situations like will limit the availability of supervised examples. Okay, on like to give you one example, like on the other hand, collecting unlabeled data might be very cheap. I can give you an example. Think about speech analysis or speech synthesis. I don't think speech synthesis is the right word. Let's just say speech analysis. Okay, but the idea here is like I'm going to give you a speech signal as input, and I want you to tell me what the corresponding text is. Whenever I'm speaking, I'm giving you the audio. Given the audio, you have to generate, let's say, the caption, automatic caption for the audio. Okay, now if I have to collect training examples for supervised learning, I have to take thousands of hours of text, like speech, ask the human to sit and manually write the corresponding text, and then train a supervised learning system, right? On the other hand, I could just download entire podcast in the world, which is like probably hundreds of thousands of speech data, right? Now the problem is I have only the speech, I don't have the corresponding text, right? So this is where the idea of semi-supervised learning comes into picture. So the idea of semi-supervised learning is we are going to have a bunch of labeled data. Okay, so let's just call that as XLYL, which is a bunch of XI, YI, for I is equal to 1 to capital N. Okay. Now we are also going to have a bunch of unlabeled data. Okay, we are going to call this as XU. There is no Y here. Okay, so this is going to be a bunch of XJ for J is equal to 1 to capital N. Okay. When you are training, I give you access to both labeled data and unlabeled data. At test time, I give you X test and you make a prediction. Is that clear? Usually, N is going to be much lesser than M, which means you can get lots and lots of unlabeled data, but very little labeled data. Okay. We are going to call this a semi-supervised learning because there is supervision for some of the data points, but there is no supervision for the rest of the data points. Now, this is the problem. Okay, so I will let you think about how to take an existing supervised learning algorithm like logistic regression or neural network and design a solution which incorporates not just the labeled data but also unlabeled data. Okay, is that clear? Is the problem clear? Any question?
What do you do with unlabeled data?
Okay, that is the solution, right? So maybe we can talk about solution just for this, like to give you an example. So what can we do with the unlabeled data? Yeah.
It depends on the imbalance or the level of imbalance between the two data sets. If there is some proximity between the labeled data and the data, start by KNN or something like that.
Yeah. Yeah. That, so here we have the first algorithm for semi-supervised learning, right? Like, so you can take the unlabeled data set, see if any of these examples is close to one of these labeled data points, and then you label this unlabeled data set, right? Now, well, I can give you, okay, just for this problem, I'm going to give you many solutions, okay, to let you know how to think. So is there any other solutions? Like, so that is a good solution, like any other solution? Yeah.
I can do a solution with like part of speech tagging. You can like try to get a bank of words and identify similar words to augment your unlabeled training set.
Okay, you can. Oh, you're creating unlabeled data there, or you're creating more data there?
No, you're taking an unlabeled data and you like matching it to the keywords.
Okay, okay. So you take the unlabeled data, like let's say you're doing part of speech tagging, then you find similar words and try to label. So essentially, like you're both trying to label the unlabeled data, right? Like so, by some heuristics, right? Like so, we can do a lot of other interesting things. Like so, for example, I can take this entire unlabeled data and like just learn a representation, like by using say autoencoder, right? I'll get a very good representation. So then I will use my label data set in this projected space. So we are going to get better performance because of the sample efficiency. You have, once you have good representation, the problem might become easier to solve, right? This is another solution. Any other solution? So there are also, yeah.
I'm just using unsupervised methods, but in the end it comes to just putting clustering the data, then putting a label on it based on how close they are to.
Okay, yeah. So that is again kind of labeling idea. Like the idea is to use any unsupervised method like clustering to cluster the whole thing, and then like see like which labeled data is close to the unlabeled data. So that is another idea. Yeah.
Use the whole data to try to give weights to the labeled data overloading to try to estimate if.
Sorry, can you repeat?
Well, you can predict weights, the weights to the example, like an example is rare. You can give it more weights to.
Okay, so that is the reverse of these solutions. Like so, based on unsupervised data, maybe try to find a weight for these labeled examples on how rare or how important they are. Yes, you can do that. So there was another, yeah.
I can do like what they do in NLP to like train vocabulary maps. They do like a where like they hide words to get a good mapping interface.
Yeah. So there are also like some other classical approaches in semi-supervised learning community, like there's something called self-training, where the idea is you train your classifier with the label data set. Okay. Once you finish training the classifier, then you use that classifier to predict labels for this unlabeled set. Okay. Now, out of all these predictions, pick the most confident predictions, put that to the training set, like labeled set. We're incrementally growing the labeled set based on prediction. Like now, there are many solutions. Like so, this is also a big field by itself. Okay, so that is the first problem. Now, the second problem that I want to talk about is the problem of structured prediction, which is generalization of the prediction problem that we have seen so far. Okay, so far when we talked about prediction, we had this idea of a single X vector going to the system, and you're making a prediction which is probably a Y vector, right? Now, instead of that, like what if you have to predict some structured output? Okay, so by structured output, like so what do I mean? Like so, for example, like what if you have to predict a sequence or a tree and so on, right? That is the idea of structured prediction. So now when you are making a prediction about a sequence, you can exploit the fact that this is a sequence and improve your prediction system. Okay. Similarly, when you are predicting a tree, you can exploit the fact that you are predicting a tree. To give you some examples, for example, let's say we want to do machine translation. Given a sequence of words, I want to predict in English, let's say, I want to predict the sequence of words in French. Okay, so here the output Y is going to be a bunch of words, W1, W2, W3, W4, and there is actually relationship between these words, right? Like it's not a random bunch of 4 words. It forms a valid, grammatically correct sentence, right? Like so. Now this is an example for structure prediction. Like an example for the tree is like for example, parsing. Okay. In parsing, like given a sentence, you want to construct a parse tree for the sentence. This is a classical NLP task. Another example that I could think of is optical character recognition, OCR systems, like which are one of the earliest applications of machine learning, real life applications of machine learning, like check reading systems, like where you put the check inside the machine, it reads how much money to which account and so on, right? Like so, in OCR systems, like you will have this image which has a bunch of numbers, like for example, postal code. Like so, like when you write your postal code, like nowadays we print things, like but in the past, like when you write your postal code, right, like something like H2X1 L2, let's say, in your postal card, there will be a sorting system which scans and predicts that, oh, this handwritten characters correspond to H2X2LP. So 1L2. Okay. Now, this is an example where you have a sequence output. And the other example that I can think of is protein structure prediction. Like where given some information, you want to predict the graph structure of the protein. Okay, there are a lot of interesting scientific applications where structure matters, and like how to come up with machine learning algorithms which will predict the structure instead of just predicting one output, right? Like so that is the idea of structure prediction. So, and again, there is a lot of interesting work in structure prediction, and there's even a course on structure prediction at UDM, like which is usually offered in winter. But to do that course, you should first do graphical models. So there's a dependency. Okay, so we'll move to the, any questions about structured prediction before moving to the third problem? Okay. Well, probably we can take a break now instead of stopping in a few minutes. We will start at, well, I think we can start at 2:45. It's fine. So we'll start at 2:45.